Okay, going on to the next segment, mass and weight, right? Now, is mass the same as weight? Okay, certainly not in physics, right? What is mass? Mass is a measure of the amount of matter. Okay, mass is the measure of the amount of matter in a body. Okay, which means that, right? Basically, simply put, it's like the number of particles present. Okay, but saying that it's just number of particles is not enough because particles can differ in their sizes, right? So if it differs in their sizes, that's why we use the word here is the measure of the amount of matter. Okay, mass is a scalar quantity, which means that it only has magnitude. Okay, the SI unit of mass, something that we already know, kilogram, okay, or kg. Okay, then what is weight? Weight is a force, right? It's a gravitational force acting on a mass, on an object that has mass. So if an object don't have mass, will there be a force? If an object don't have mass, right? Will there be a force? There won't be, okay? There will not be a force, okay? Or there will not be weight acting on it. There will not be a force or weight, okay? So weight is a vector, right, which means it has magnitude and direction, and the SI unit is Newton, okay, with a capital N as the symbol, right? So to link between mass and weight, what is weight? Okay, it actually is simply the effect. Okay, weight is simply the effect of a gravitational force acting on an object with mass, right? So the weight is just a effect of a force, okay, acting on the mass. Okay, now to explain um, forces, okay, in physics we use this concept as a field, right? Uh, a field is like a region, it's like a space, okay. Now it's just a region in which a mass experiences a force due to gravitational attraction. Okay, so within this space, for example, the Earth, right, because of its large mass, it will exert influence on the space. Okay, so all masses, for example, you and me, we have mass, right? We will experience a gravitational attraction towards the center of the Earth, right? Towards the center of the Earth. Okay, and the force that we experience, right, will be pointing downwards towards the center. Okay, so all object will experience a gravitational force in the gravitational field, right? Remember, a field is just a region, a space, right? And all object also creates right? We also create a gravitational field ourselves. Okay, all object with mass, right, also create a gravitational field. But because of our small mass, right, compared to the Earth, right, our field is very weak, right? So for example, between you and your classmate when you are sitting beside each other, okay, let me draw it out, right? Between you and your classmate, actually both of you will also experience gravitational force from each other. Okay, because anything that has mass will create a gravitational field also, right? So you will exert a force on each other, but because our mass is too small, so this force that we experience will be very little. Okay, almost zero. Force is too small to be experienced. Okay, because we have our mass is not enough. Okay, so how strong, right? How strong when we describe a field, how strong it is, right? We will use this term that's called the gravitational field strength. Okay, now this is defined as the gravitational force per unit mass acting, or rather, sorry, unit mass placed at that point. Okay, now please take note that at that point, this is a keyword, right? You must include this because, right, now if you look at this field, and if you were to think logically, the further away you are from the field, right, how do you think the gravitational force will behave? Okay, the further away you are from the further away you are from the Earth, the smaller the gravitational force. Right? It makes sense, right? Right. So within this field, the further away you are from the center, the weaker the force is. Okay, so that's why you need to put in this line at that point because at different point, the field strength will be different. Okay, at different point, the gravitational field strength differs. Okay, now in equation form, how do we calculate gravitational field strength? Based on this definition, force per unit mass, right? Which is just your weight divided by mass. Okay, now how do we find what is the SI unit of gravitational field strength? Weight is just Newton, mass is kg, so the SI unit for gravitational field strength is just Newton per kg. Okay, that's why over here, this is the SI unit. Now, what is the gravitational field strength of Earth? It's actually a constant value of 10 Newton per kg, right? Anywhere that is near the surface of the Earth, we will have a constant value of 10 Newton per kg. Right? Whereas for Moon, you will have 1.6. Now, what does this 10 and 1.6, what do they mean? Right? It actually just represent for every kg of mass, I will experience 10 Newton. Okay. So for example, 1 kg of object will experience 10 Newton, right, on Earth. Whereas 1 kg of object will experience 1.6 Newton on the moon. Right, so what this means is that if you are on the moon, you will experience, if you, let's say you jump, you make a jump, right, you will realize that you can jump higher and you will fall back to the surface of the moon much slower. Okay, now how do we adjust the equation, right? Let's say we want to find the weight. Okay, so based on this, G equals to W over M. If I want to find what is weight, which is most of the time, we do this. So weight is just equals to M times G. Okay, in terms of the math, just to do a quick one, right? You can do a cross multiplication. Okay, you times M on both sides, right? Then this will give you mg equals to W over M times M, right? Then the M will divide off each other. So that's how it becomes W equals mg. Okay, so from mass to weight, you just need to multiply by G. This one you just need to divide from weight to mass. Okay, for example 2, right? To find the weight of each of the object, right? To calculate the weight from each of the object. So weight of iPhone, right, is equals to 135 grams, right? Sorry, before that, you need to consider, since this is gram, right, it's not in the SI unit, you need to convert this to SI unit first. Right, so this is 0.135 kilograms divided by, sorry, not divide, 0.135 kilograms times 10 Newton per kg. W equals to mg. Okay, so this gives you 1.35 Newton. Okay, for baby elephant, this is equals to 100 kilograms times 10 Newton per kg. So this gives you 1000 Newton. Okay, last one, weight of double decker bus. This is equals to 2400 kg times 10 Newton per kg. Okay, 24,000 Newton. Okay, I'm gonna just briefly talk about this. The gravitational field strength near the Earth's surface is 10 Newton per kg, and this is equals to the acceleration at free fall that you learned in chapter 2. Okay, now the detail of this is not very important, but you just need to know that they actually mean the same thing, right? Even though their units look very different. So if I'm talking about acceleration, make sure you are using this unit, meter per second square. If I'm talking about gravitational field strength, then you have to use Newton per kg. Okay, this will be the next segment.